Hello, folks. I will be doing a sequence of video tutorials on the concept of optimization in Catia V5. Now, this first one is going to be some preliminary aspects of optimization and exactly what do we have in mind. Uh, and I will not be doing any specific Catia examples. However, at the end of this tutorial, I will show you 4 or 5 examples that will be doing, but they will be not part of this tutorial. It will be part of the subsequent ones. Okay. Now, before I go through my transparencies and talk about these things, I want to tell you where this workbench is actually located. So if you look at Start, and you go down, you scroll down to knowledgeware, and in knowledgeware you see several things. The specific one that we are interested in is this product engineering uh, optimizer, which I will refer to it as PEO, product engineering optimizer. That's where it is. Okay. Now, having done that, having shown you that, I will go through my slides. So let us uh, start from slide number 1. I'm sure during your education or your work experience, you have heard on numerous occasions about the concept of optimizing something. So you're told, okay, you came up with a design, now can you optimize it? Exactly what does that mean? Well, this expression is very loaded in a sense that it means different things to different people. Okay? Now, probably the first time that you ever heard of this was when you took your first calculus class, where you were supposed to find the maximum or minimum of a function of, let's make it simple, single variable x. And you remember that you were told that, okay, take the derivative, set it equal to 0, and then solve for x. So this was the strategy that you were told you were shown in your first year calculus class. Now, if you do this and the function f of x is nice and smooth like that, so that it does have a derivative, then when you set it equal to 0, you're talking about this particular peak, okay? So obviously, if you look at this peak, compared to the points around it, it has the highest y value, the largest y value. Okay. Now, the question was, well, what if my curve looks like this? Then this business of taking the derivative and setting it equal to 0 does not make sense at this peak because there is no derivative there. Okay? So you cannot even talk about df dx equal to 0. And the difference between this problem and the previous one was that there was a derivative, and that derivative there could actually be set equal to 0. Okay. Now, let's make it a little bit more complicated. So suppose the function f that we have looks like this. Notice that based on the discussion that we had, at this point, at the point in the middle peak right here, okay, df dx is 0 because it has a horizontal tangent line. But if you look at the point on the left, df dx doesn't even exist. So you cannot even talk about df dx equal to 0. As a matter of fact, if you were given this particular graph, notice that this point, the point on the right, which has the biggest height, is in fact what we may be looking for, and it has nothing to do with the derivative. Okay? So you've got to be careful about what do you mean by optimize? Or do you mean the point on the left? Do you mean the middle peak? Or do you mean the one on the very right? Okay, so the ones on the left, these are called local optimized points, but the global one that you may be interested in is way at the right, and it has nothing to do with the FDX. It has nothing to do with derivative. So when you're asked to optimize something, it has to be very clear in your mind, what is it that you're trying to Fine. Now, generally speaking, when you're asked to optimize something means find some value of the design parameters, things that is under your control, so that something is maximum or something is minimum, etc. But these are physical variables that you're trying to play with. Therefore, there is a range. There is a range. So it is very important for you to look at the range of meaningful interval for the parameters that you are trying to find. It could be, for example, let's hypothetically say it's the length of a screwdriver. Well, the length of a screwdriver is not going to be 10 miles. Usually screwdrivers, okay, can be very tiny, but mean maybe 5 or maybe or 2 inches, perhaps a screwdriver for fixing your glasses, or it could be a screwdriver which is, you have seen it probably in mechanic shop, which could be as long as maybe 2 feet. So the range of the values of the thing that's under your control, which is, for example, X, the length of the screwdriver goes from 2 inches to, I don't know, maybe 20 inches or something like that. You're not going to look everywhere. Okay. Now, after you took your first calculus class, in the second one, maybe in the second year, you were you were you were facing the same type of questions, except that the function of interest was a function of more than one variable, a two variable, for example, x and y. And once again, you want to find the maximum or minimum of this thing. Now, remember, the whole idea, as in the one-dimensional case, a one-variable case, is to find a partial derivative and set it equal to 0. By the way, these things are called finding the critical values, but they may not give you the maximum or minimum. Now, same statements that I made about the sharp corners and wedges and things like that applied here too. Okay. Now, in the same course, probably after you did the basic stuff, you were given a type of problem where you not only had to find the maximum or minimum of f, but you were given some constraints. For example, yes, maximize or minimize f of x and y, w, but there is a relationship between them. The way we handle these things, or you handle these things, was through the concept of Lagrange multiplier. There are other ways of doing it, by the way. Lagrange multiplier is not the only one, but and in that process, you may recall that you define something called L, which is your Lagrangian, in other words, f plus lambda times g, except that we don't know what lambda is. And then you take all the partial derivatives of L with respect to x, y, and lambda, set it equal to 0, and you solve for x, y, and lambda. Hopefully, it gives you the maximum or minimum. By the way, it may give you neither one, but anyway, this is the technique that you used before. Now, these methods are called gradient-based methods, these algorithms, because they involve finding derivatives or partial derivatives. Now, they are available in the product engineering optimizer, but I will not use it in my video segments, because there is something else that is called a different algorithm, which does not actually find these derivatives, and it's called simulated annealing algorithm. It's a robust algorithm that is widely used, and what I meant here, of course, nothing is foolproof, okay? It works in many cases, but there are there are places or type of problem that it may not completely work. Okay, now let me remind you where this product engineering optimizer was. I said you go to the start and scroll down to the knowledge product engineering optimizer. By the way, these top two, I have used it in other tutorials for a different purpose, but it doesn't pertain to the present video segment. So right there, okay. And when you select that, a dialog box opens up, and notice that there's certain things that you have to specify. For example, what are your free parameters? What are the things that you're allowed to change? And you are trying to find value or values of those parameters, which minimizes or maximizes or something. Okay, this is minimized, but you can change it to maximize, or there are other things that you can do. And the algorithm that is being used is can be gradient based. Okay, gradient based can be simulated annealing. Okay, all my examples that I'm going to show you are based on simulated annealing. Okay, now these are the examples that I'm going to be doing in subsequent video segment. Each one of them will appear in one segment. So we have this. This is just a rectangle. You can think about it in the surface, etc. And you're trying to maximize the area. You're trying to find the values of A and B where the area of this thing is maximum, but the perimeter is constant. So if you look at area equal to A times B, and the constraint is 2A plus 2B equal to, for example, 20 units, inches or millimeter, whatever it happens to be. Okay. Now, but remember, A and B are really physical, in all likelihood, physical problems, physical quantities. Therefore, there is a range associated with it. Okay. Uh, for example, look for your solution where A is between 0 and 6 and B is between 0 and 6. In this particular problem, there is a unique value of A which will give you that value, but there may be problems where there are multiple values. This is the second problem that I'm going to do. So we have a box here. Some of the dimensions are fixed. The height is your design, one of your design free parameters, and the thickness is one of your thickness is also the second free parameter. So we have two free parameters, T and H, and two fixed dimensions here, which are given down below. Now we are trying to find H and T such that the capacity, the volume of the enclosed area, enclosed volume is 45,000 cubic millimeter, and the height and the range of the H and T, the thickness and the height of the box is between in these ranges, 3 millimeter, 0.5, and 35 millimeter, 15 millimeter. Now, this is not this is not a maximizing or minimizing problem. So it's unfair to say that, we optimize. This is not really an optimization problem, but it's a target value problem. In other words, give me a T and an H where the volume of this thing is 45,000 and it fits in this range. Okay. Here's another one. We have a wiper blade, which is a wiper blade of a car, for example, and shown on the left, and some dimensions, these dimensions, OA. Let me see now. OA, AB is here. OD, which is the distance from the revolute joint all the way to that location. Alpha, beta, and gamma are to be found. So there are 6 free parameters, and the other dimensions are fixed. For example, the dimension of the wiped area is the dimension of the thing, the rectangle is fixed, etc. And you're supposed to find these design parameters. So, let me go back to this. So that the percentage, maximize the white area percentage. In other words, the area of the green over the area of the fixed rectangle is times 100 to get percentage is maximum. Okay. Final one that I will be doing is a finite element problem. So notice that we have a bent rod here. The some dimensions are fixed. For example, this dimension, the dimension of this this little piece here, 70 millimeter is fixed. The radius of the curvature of this bend is fixed, but your job is to find an L and an R, the radius of the bar, so that it falls into that range, and so that the when you load it with 2000, for example, Newton downward, the mesostress, one mesostress, and the displacement are given under this constraint, and the weight of the bar is minimum, bent rod is minimum. Okay, so here we're going to have to do combination of finite elements and the PEO, or product engineering optimizer. Okay, so this is what's going to happen, and I hope that you found it useful, and look at the other videos, see what you can do. Bye.